we'll start. All right, so hello. I presume you're all here for 16020, like I asked before. So, yeah, there's not really good ways to do social distancing, so you can just sit there or find a spot and we'll call it good. Anyways, so let's go ahead and get started. So just to start, switch to PC. Hi, my name is Tim. Like I said, I'm going to be your substitute instructor for the next few weeks. We're covering for Paulo Kupek. His email is speakkupek@purdue.edu if you have any questions, or you can also email me if you have any questions at tworley@purdue.edu. So I'm the substitute instructor, but he will still be holding office hours on Piazza, so just keep a lookout for that. And the course webpage is located at this URL. You put it Bright Units. There's also the Brightspace and Long Kappa pages for the course as well, so please be aware of that. Email etiquette. When sending an email, please adhere to the following. I forgot to add this. So look at course webpage or Brightspace. Sorry, Blackboard was the old thing. For information before sending emails, most anything you need will be located there. Include a subject line encompassing what the title is about. Keep the email short, sweet, to the point. Send an email with both your first and last name so I know who I'm talking to. And grades cannot be discussed through email. Course calendar. So the calendar shows dates that lessons will be covered and exam dates and times. And all homework will be completed and graded online using Long Kappa. No assignments will be turned in and hand graded like 16010. But the difference with this class now is that homework is usually due at 7:59 on the day of the next lecture. So for instance, the content covered today is going to be due this Friday, so 2 days from now at 7:59 a.m. And homework 0, which is basically just make sure you type stuff in Long Kappa correctly, is due tomorrow at 7:59. So I won't go over that in class because you guys have already had enough experience typing stuff in Long Kappa and 16010, so I won't discuss that here. That should just be a review anyway. Online homework. All homework will be completed in Long Kappa, as last semester. Generally, extensions will only be given in extreme circumstances. See syllabus for more information. If you know your schedule is busy at certain times, make adjustments to complete the homework before the due date. But to compensate for that, the three lowest homework scores will be dropped at the end of the semester. Now, here's the big difference with 16020. Most problems are going to like 10 submissions as opposed to 99. So just keep that in mind while you're doing the homework. But matching, true, false, yes, no, multiple choice, and a few others of similar nature will have a limited number of submissions, usually a little less than 10. Okay. More hints. As you probably have seen in 16010, do not round unless the problem explicitly tells you to. If you need to estimate, never round early in the calculations. Only do that at the very end. Use all the decimal places that the calculator gives you. Pay attention to upper or lower cases when entering variables. And if you have to enter your answer in interval notation, make sure to write from the lowest to highest values, such as 2, 5, and 5, 2. More hints. Use the practice entering expressions in Long Kappa link in the homework tab. That's going to be homework 0, like I said. So another thing with this semester in particular is that you will need to take advantage of the Piazza forum because a lot of the problems in this class are going to be pretty difficult compared to 16010. So just keep that in mind. On that note, to prepare for quizzes and exams, one good tip is to write up homework solutions while doing the homework, as certain homework problems, as you will receive very quickly, are going to be pretty involving. Quizzes. At least 14 quizzes will be given. And the first quiz, by the way, is next Monday, covers lesson R, so today's lesson. They're worth 10 points each. They're individual quizzes, and unlike 16010, they will be in person. So what I'm going to have you do is, when you're done with your quiz, leave them face down, and then I'll pick it up. So, and if you need to isolate by Protect Purdue policy, Pablo will get an email about that, and he'll exempt you from quizzes that you'll miss. I haven't quite told him that yet, but I'll coordinate that with him a little bit after this class. protect Purdue. If you are sick, have COVID, obviously don't come to class. And you're all wearing a mask, good. But failure to comply may result in dismissal for the whole class, so please don't be that guy. I would very much appreciate that. So midterms. So there will be 4 midterms. Please mark the following dates for the exams. So first one will be on February 8th at 8 p.m., covering lessons R through 5. The next one will be on March 3rd, second on March 3rd, third on March 29th, and then the fourth on April 21st. Exam conflicts. If you have a conflict with one of the exams, like for instance, if you have an evening class, you have another exam during that time, or you have to isolate, you need to notify the course coordinator as soon as you can, because he will set you up with an alternate if you have a legit reason to do so. If you miss the exam and you do not notify the course coordinator in advance, notify him within 24 hours from the exam and he might give you an alternate. So email him, in this case, Pablo, so since he's your instructor. Final exam. There will be a comprehensive final exam during the last week. We don't quite know when that is yet, but just be on the lookout for that. Calculator policy. So in this case, we will be strict about the calculator policy in this class. So you will need a one-line calculator here, like a TA30X study. So you're not going to be able to get away with a 2-line calculator or a graphic calculator this time. Because you will need that for quizzes and exams. So check the web page for more specific calculator policy. Supplemental instruction. At the time of writing this, I just said, okay, well, that's still up in the air, but the Brightspace page talked about that a little bit in more detail, so I would say refer to that. Academic adjustments. If you have been certified by the DRC as eligible for academic adjustments or quizzes, see math.purdue.edu/ADA for exam and quiz procedures for Math 1 6020, or contact Stephanie Foster at that email, foster80@purdue.edu. Grades. There are going to be 800 points available in the course. So quizzes and homework will be in total worth 60 points. And the 4 midterms will be 120 points, with the final being 200. So possible campus emergencies. So in the event of a major campus emergency, course requirements, exam dates, deadlines, and grading procedures are subject to change due to a revised semester calendar or other circumstances. Visit the Math 1 6020 website if you have, or contact the course coordinator with questions. So any questions? Yeah.
Our exams are online, right?
No, they're going to be in person like the quizzes. But like I said, if you have to isolate, that counts as a legitimate excuse to miss the exam. So notify the course coordinator if you are in that situation.
So I'm like new to Purdue math. What is Piazza?
What's that?
Like Piazza? Like
Piazza?
Piazza?
Yeah. Did you take 16010 last semester?
No, last time I took math was BC in high school.
Okay. I think there's a link on the main course webpage, right? If I recall. Okay, yeah, just type the course webpage and you'll see it.
Okay.
Any other questions? Cool. All right, so let's talk about some good old Lesson R review. So this is mostly just a review of Math 1 6010 stuff, so most of this stuff will be pretty familiar to you. So if you guys have your outlines, I would recommend taking those out, or if you have a notebook, that works just as well. So let's go ahead and get started with the first lesson of the semester. So recall derivatives. They tell how much f of x changes, f of x is a function, of course, with respect to x. And as you probably already noticed, I'm a lefty, so unfortunately there's not much I can do about that, but I'll try to accommodate as best I can with that. So just heads up. So 2 ways to view integration. So the first way, as we've seen in 16010, is indefinite integration, which essentially just it's sort of like undoes differentiation. It undoes differentiation. abbreviation. Okay. So to see what I mean by this, so definition, an antiderivative of f of x is a function, capital F of x, with such that if you take the derivative of capital F of x, you get little f of x back. Okay. Or another way to write this is we can say that the integral of f of x with respect to x equals f of x plus some arbitrary constant c. That's the second way to write that. So c is an arbitrary constant. Okay, so to get a quick idea of what I mean by this, let's talk about the power rule right quick. So, if we recall from Cap 1, let's see what that was. So if we take the derivative with respect to x of x to the n plus 1, then if we use the power rule on this guy, does anyone remember what the power rule for derivative states? Yeah, so you take the power up here, you multiply it here, right? And then it's x to the what power?
X to the n minus 1.
Well, this quantity minus 1, right?
Yeah.
So essentially just x to the n, right? Okay. So you're probably familiar with the, x to the n derivative is n times x to the n minus 1, but the reason I wrote it like this is so we can get the antiderivative power from this. So as a result, one way we can rewrite this using this notation here is, that's just saying the integral of n plus 1 times x to the n dx is equal to x to the n plus 1 plus c. Okay? So what that tells us is, okay, so we know that we can take this constant n plus 1 outside. So what happens if we do that? So if we divide both sides by n plus 1, then what do we end up with? So we have x to the n dx. That's going to equal, so you're essentially just dividing this whole thing down here, over here, by n plus 1. So you have x to the n plus 1 over n plus 1 plus c divided by n plus 1. Okay? So what that tells us is, okay, well, the good news is c is an arbitrary constant, as we established, right? So one way we can view this arbitrary constant is we can say, all right, since this is constant, we can allow c to, quote-unquote, absorb this n plus 1 thing. So essentially what I'm getting at is x to the n plus 1 over n plus 1 like we have, but then plus c. So I can just rewrite this expression here as this. So like I said, so c is arbitrary. So absorbs, quote unquote, 1 over n plus 1. Okay? See if I can zoom in on this. That's better. Can you guys see better now? Okay, cool. So what that ultimately tells us is that, all right, well, the integral of x to the n dx will be x to the n plus 1 over n plus 1 plus c. But then if we look at what this expression here says, this holds provided that n is not equal to what number? Negative 1, right? Because if n equals negative 1, well, we have is divided by 0 here. So this is our antiderivative power. Okay. So that's the antiderivative power rule right here. But the nice thing is that other basic antiderivatives also come from basic derivative rules. So, for example, for instance, if we have the sum slash difference of two functions, and we wish to take its derivative, this is the same thing as taking the derivatives of the two individual functions, f and g, and then add, subtract as necessary. So we have f of x plus or minus g prime of x. Okay. So the reason I wrote this is because now we can rewrite this using this notation here with antiderivatives. So what I mean is we have f of f prime of x plus or minus g prime of x is equal to f of x plus or minus g of x, and then, of course, your plus c arbitrary constant. Now, the reason why this is so important, despite its seeming abstractness, is because this allows us to integrate. We can integrate term by term. So this is why this rule is so important. So just keep that in mind. All right. The second rule I wanted to discuss, or / remind you of, so if b is a constant, b is constant. So if we have some constant times f of x, and we take its derivative, then remember, how can we rewrite this? So this is the same thing as saying, okay, let's just take that constant, b, and then times f prime of x. So as a result, we can then say, all right, this is the same thing as b times f prime of x dx, derivative of this. We can, like I said, we can just take this constant outside now. So we have b times the integral of f of x, or sorry, f prime of x dx. So that consequently equals b times f of x plus c. Okay. So there's that. And two more I wanted to get at to sort of help you establish the idea of this is we can say, all right, let's focus on sine of x and cosine of x, their derivatives. Now, just as a quick review from Math 16010/Calc 1, what are these two derivatives? So what are the derivatives of sine and cosine? Anyone remind me real quick? Right, so derivative of sine is cosine, and derivative of cosine is negative sine of x. Okay? So by similar reasoning that we established up here, well, you can pretty quickly get that the antiderivative of cosine, well, that's just sine of x plus c, right? But then, what about this guy? So what does that tell us about the antiderivative or integral of sine of x? Yeah, just negative cosine, right? Then, well, negative cosine of x plus c. So those are just some of the basic ways we can sort of extract some of the basic antiderivative rules from the derivative rules we've already seen last semester, or whenever you took Calc 1. So from there, you get the idea, right? So I'll just say and so on, because if we look at the next page, you notice, that I have a lot of these antiderivatives ready to go. So if we use a similar reasoning that we utilized up here, well, you can get a lot more of these basic antiderivative rules that we saw in Calc 1. So that's one nice thing to keep in mind for these types of problems. Okay, so any questions on that before we get to actual examples? So let's get to example 1 then to get a pretty basic idea of what's going on. So to look at example 1, we have evaluate 6 times secant of x times secant of x plus 5 times tangent of x. Now, if you look at the rules that we've established on this, well, it doesn't really seem like there's a good way to work with this expression exactly. So, what do you think we'll need to do with our expression inside the integral to make things a bit easier on our...
We can break up the integral into two different integrals and then just add them together.
Well, right idea, but we can't do that immediately with this. So what do we have to do first? Yeah, we got to distribute this 6 times secant of x, right? Because if we do that, then we have integral of 6 times secant squared of x plus, in this case, 30 times secant of x times tangent of x dx. Okay? But then, like you said, now we can break it up using this rule right here. You recall from last page. So then what we get from this is, well, we get 6 times secant squared of x dx plus 30 times secant of x tangent of x dx. Right? Okay, so from that we say, all right, well, that's good and all. So now we got to break this up a little bit more, because now we have, okay, well, by our rules here, we have the antiderivatives of secant and secant of x times tangent of x. So what would the corresponding derivatives of these two things be then, using the rules we've established up until this point? So, for instance, we already know what the integral of secant squared is. So, consequently, what will be the antiderivative of 6 times secant squared? 6 times tangent, right? Because, like we said, we can take the constants outside, right? Secant squared of x plus 30 times secant of x times tangent of x, right? And then we have our antiderivatives. So we have secant squared its antiderivative is tangent, and then plus 30 times the antiderivative of secant times tangent, which is secant. So we have secant of x. And then the last thing we need, of course, is 1, 2, 3. Plus c. Good. Now, remember, the one thing you need to remember with indefinite integration is never, ever, ever, ever forget plus c. So I'll write that here. So I put that in all caps just so you guys make sure to remember. So never forget plus c. And I'll use some exclamation points to help you remember that. Actually, you know what? Screw it. Here's a few more just to make sure you guys remember. All right. So that's example 1. So any questions on that? So thankfully that wasn't too bad. That was just a pretty nice quick refresher on Calc 1, so nothing too crazy with that. Example 2, though, is where things get a little more interesting. So with this one, we have y prime of x. We already have the derivative of some function whose derivative equals x squared minus 1 all over square root of x. And we're given that y of 4 equals 3. So we have to find y of x from this. Okay? So one thing to note here is that, well, because we need to start from the derivative and work our way backwards, well, that should be a pretty good indicator that we got to take the integral of this expression here, right? But here's the problem. We don't really have a quotient rule for antiderivatives. So we gotta find some way to manipulate this before we can actually start taking integrals properly here. So what would you recommend we do with this before we go any further?
Separate the fractions into 2 separate fractions.
Exactly. So we have y prime of x equals x squared over square root of x minus 1 over square root of x, right? Okay. So then if we try to simplify these, it looks like we can get both of these expressions here as x to some power, right? So with x squared over square root of x, for instance, what would that simplify to using our exponential rules we should hopefully be familiar with?
be x to the 3 halves.
Bingo, right. Because remember, this is x squared over x to the 1/2, right? So this is just x to the 3 halves. And then similarly, 1 over root x is x to the what power? Negative 1/2, good. All right, great. Okay, so now we can go ahead and take the antiderivative of this thing. So if we do that, we have y of x equals the antiderivative of y prime of x, right? So all we got to do now is figure out, all right, well, what's the integral of x to the 3 halves minus x to the negative 1/2 dx, okay? So now this is where it looks like our antiderivative power rule is going to come into play here, right? So in this case, you're going to have to use the antiderivative power rule from the last page with n equals 3 halves and then n equals negative 1/2 respectively for each term. So if we use that, I'll help you with the first one to give you an idea of what's going on. So we have x to the, well, let's see. You have to essentially add, if we go back to our rule here. If we go back to our rule, we notice, all right, well, all we really have to do is just figure out, all right, well, in this case, n is 3 halves, so all we really have to do is just add 1 to it and then make that our new exponent and then divide by that same number as well. So if we have 3 halves plus 1, well, that's just 5 halves. And then over 5 halves. Okay. And then minus, well, if we do the same thing with negative 1/2, what would we end up with here? So, yeah, we're just going to have positive 1/2, right? Okay. So we have that. And then if we use properties of, if we notice that dividing by a fraction is the same thing as multiplying by the reciprocal, we can pretty quickly see that this is just 2/5 x to the 5 halves minus 2 times x to the positive 1/2 and then plus c. C. Okay. So the good news is that now we have what's known as the general solution to this problem. So this is the general solution. As it involves plus c. Okay? So now we say, all right, that's good and all, but now we have to actually figure out, well, what is y of x exactly? Because here, if we just had this antiderivative and we did not have this extra data, then this is all we can really do. But now we have y of 4 equals 3. So now we have to actually figure out what c is. So like I said, use y of 4 equals 3 to find c. Okay? So like I said, this is the general form of y of x. So all you have to do now is actually figure out what the actual value of c is here. Okay? So if we use this data to find c, this will give us what's known as the particular solution. Particular solution. Okay. So if we do that, if we let x equal 4 here, then we have y of 4 equals, let's see, 2/5 times 4 to the 5 halves minus 2 times 4 to the 1/2 plus c. So now at this point, definitely seems like we're going to need to clean this up a bit before we set this equal to 3. So what does this first term simplify to if we use either our calculators or try and simplify using exponential rules? First off, what is 4 to the 5 halves going to equal? Not quite 16. 32, right? So if we multiply it to 2/5, we should end up with 64 over 5. Okay? And then you have 2 times this 4 to the 1/2, or square root of 4. So that should pretty quickly give you, this is just minus 4 plus c. Okay? So this equals 3 because of our assumptions here. So what you'll notice from this is that, okay, so if we solve for c from this, we have that c equals, let's see, 3 plus 4 minus 64 over 5. So if we simplify all that and clean this up into one fraction, then your calculator will give you, this is just negative 29 over 5. Okay? So, as a result of this, now we have the exact value of c here. So now we have that y of x equals 2/5 x to the 5/2 minus 2 times x to the 1/2, then minus 29 over 5. And now we have the particular solution that we were trying to figure out in the starter problem. Okay. So, any questions on any of all this? So you're all, yeah?
So like on a quiz and exam, if you wrote the final solution as like minus 2 to the square root of x, will you get points deducted?
Minus 2 to the square root of no.
Okay.
So on a quiz, I won't be that harsh, but exams are usually multiple choice, so I would say just watch out for that. Okay. Any other questions on example 2? Looks like you all are done writing that down, so I'll go ahead and move on to page 3. Okay, so that's all I really wanted to say on indefinite integration. Now let's move on to, well, definite integration. So, definite integration is the second way to view integration, as we have in part B. So, way to measure this is basically area under a curve, or also measures accumulation. Okay? So for these types of definite integrals, we always need one of two things. We need an interval or an upper / lower bound. So, one thing to keep in mind for definite integration. Okay? So, to give you a picture of what I mean by this, a little bit easier to visualize. So, I'm assuming everyone's still with page 2. Cool. Alright. So, we take two values on the x-axis. Let's call them a and b, just for the sake of being arbitrary with it. Then here's our function y equals f of x. Y equals f of x. The area I'm talking about here ends up being this shaded region here. So that's the region I'm talking about. This shaded area here is the area I'm focusing on. So this is the signed area under f of x from a to b is given by this definite integral. So as before, we have to integrate with respect to f of x with respect to x, but now we have a as our lower bound and b as our upper bound to denote the fact that we are working with a definite integral. Now, if f of x is positive on this interval from a to b, then we just get the area like I said, but I'm utilizing this extra word signed to denote the fact that, it's possible that f of x may go below the x-axis, so we have to accommodate for that as necessary. Okay, and then, like I said, this is bounded by y equals f of x, y equals 0, because y equals 0 is the x-axis, and then x equals a, and x equals b. Okay? So, that's the area we're talking about. Now, if you want to be able to evaluate this definite integral, then we need what's known as the fundamental theorem of calculus, which I'll remind you guys of what that is. So the integral from a to b of, I'm just going to note this as f prime of x dx equals, and you should have seen this last semester or whenever you took Calc 1, it's f of b minus f of a. Okay. Now, you guys might be more familiar with the way of seeing this as, if we have capital F of x is the antiderivative of little f of x, then this would be little f of x here, and then capital F of x would go here in their respective positions. But the reason I'm using f prime of x here is to denote the fact that, in a lot of problems we'll see in this class, f prime of x will usually denote some sort of rate function. So I'm using the f prime of x notation here to denote that. Okay? So, any questions on that before we move on to the third example? Okay. Coolio. So, with that in mind, let's move on to example 3 then. So we have this function here. We have this linear function here, and we're trying to figure out what the area of this is. So we have what integral can be used to find the area of this shaded region below, and what is this area? So one thing you'll note here is that this is at x equals 1, this is at x equals 3, and this is at 1, and this is at 3. So because of that, you'll note some things here. So this, as you can pretty easily see, this is just a linear function, right? Linear function. Okay? And you also notice is that this is a linear function with points 0, 1 and 1, 3. With points 0, 1 and 1, 3. Okay? Now, because this is a linear function, it's of the form y equals mx plus b. So, usually with these types of problems, well, you got to figure out what is the slope first. So, the good news is that we have 2 points, so we can pretty quickly figure out the slope from this. So, using these 2 points, what would be the slope? And how'd you get 2?
3 minus 1 over 1 minus 0.
Right, you have to take the difference of the y values, so in this case 3 minus 1, over the difference of the x values, so 1 minus 0. Okay? So in this case, that should pretty quickly simplify to 2, so there's your slope. Okay? So now that we have that, then now we're going to use the point, not the point slope form, but the slope intercept form, because that's generally quicker. So if we use the slope intercept form, so if we use that, this is going to yield, well, let's see. I'm going to use the point 0, 1 just because that'll make things a bit quicker on our end. But this is going to be y minus, in this case, 1 from this one up here. And then the slope, 2, times x minus the x coordinate that we're given. So x minus 0. Okay? Alright. So then from this, if we solve for y, you should be able to pretty quickly see that this just simplifies to y equals 2x plus 1. Okay? So nothing too crazy there. That's just a quick bit of algebra. So, as a result of this, and if we use the reasoning that we established above at the start of page 3, that means that the integral that we need, is given by what? So the function that we have is 2x plus 1, so that's our function. And then based off of the picture we have, what would our bounds be? Yeah, it's 1 to 3, right? Okay. So from this, now we say, all right, well, now we have to take the antiderivative of this and then use the fundamental theorem of calculus from there, right? So using the antiderivative power rule, what would the antiderivative of 2x plus 1 be?
X to the second power plus x.
Yeah, just x squared plus x. And I'm going to use this bracket notation here to denote the fact that we are working with the fundamental theorem of calculus. All right? So, like we established we established here, all we have to do is just take our antiderivative and then evaluate first at the upper bound. So in this case, we have 3 squared plus 3. Just let x equal 3, no problem. And then minus, well, let x equal the lower bound. So we have 1 squared plus 1. Okay? So this is going to be the integral we need. And then if you simplify this, you should be able to see that this is just a good old 10. So that means that the integral we have here will give you the area of this shaded region, which ends up being 10. Okay? Oh, whoops. Okay. So, good. Oh, oops. Oh, good. Yay. Not yay. Cool. Well, let's give them a thumbs up. All right. So, moving on from that, let's move on to our last example, example 4. So, premise is that a strain of bacteria grows at a rate modeled by R of t equals 8 times e to the t, where t is an hour since 8 a.m., and R of t is the number of bacteria per hour. So, first question asks, how many bacteria develop from 11 a.m. to 3 p.m.? Round to the nearest number of bacteria. Okay? So for part A, we notice that we have these times here, so we need to convert that into the values of t that we need for our problem. So from 11 a.m. and 3 p.m. So in this case, t is in hours since 8 a.m. as per the problem statement. So what would, if we translated 11 a.m. to some value of t, what would that value of t be? So t is 11, or t is an hour since 8 a.m. 3. Okay? And then similarly, 3 p.m. corresponds to t equals 7, right? Okay? So as a result of this, we got to find what integral. So in this case, we have we have this rate function here. So another nice thing about the fundamental theorem of calculus is that this f of b minus f of a here can also represent net accumulation as we described at the top of page 3. So as a result of this, that means it suffices to find r of t dt, with in this case our bounds going from 3 to 7. Okay? Because this will give us the net accumulation here. Or in this case, / growth of bacteria. Okay? Okay. So all we got to do now is figure out, all right, well, what's the integral from 3 to 7 of 8 times e to the t, right? So first off, well, what's the antiderivative of 8 times e to the t? So, you need a hint. Look at the, yeah, go ahead.
Is it e to t?
Yeah. Yeah, so integral of e to the t is just itself, right? And then and the constant doesn't change that, right? So in this case, our antiderivative is just 8 times e to the t. From 3 to 7. Okay. So the thing is that if we use the fundamental theorem of calculus like we talked about on the last page, then the exact value you're looking for is 8 times e to the 7th minus 8 times e cubed. So this would be the exact value you need here, but remember, the problem states that we need to round to the nearest number of bacteria. So in this case, the exact value here is not going to cut it. So in this case, if you plug this into a calculator, you should end up with 8,612 if you round to the nearest number of bacteria. Okay. So like I said, I'll mention it here. So rounds only if problem says to. Okay. Okay. So that's part A. So nothing too crazy with that. But now part B is a little bit more interesting because we have to figure out how many hours after 8 a.m. will the strain gain 40 more bacteria. And we have to round to the nearest 100th here. So the nice thing is that with 8 a.m., well, that's 0 hours since 8 a.m., so nothing too crazy with that. So that's just t equals 0 in this context. But now what we're going to do is we're going to let x equal number of hours after 8 a.m. when 40 more bacteria form. Okay? So as a result of this, using the reasoning that we established in part A, we can see that the net number of new bacteria in this context, so in this sense, 8 a.m. So in this case, using the similar reasoning that we had up here, we can say, all right, we can also establish this expression here as an integral as well. Except in this case, while we still have rt dt inside the integral, in this case we're measuring from 0 since 8 a.m. and then we want to figure out how many hours after 8 a.m. when we get 40 more bacteria. So in this case, let the upper bound be x here. Okay. So because of this, the net number of bacteria we want to see is 40. So in this case, we equate that to the integral from 0 to x of r of t. So 8 times e to the t dt. So applying fundamental theorem of calculus from this, you should be able to see that this is just 8 times e to the x minus 8 times e to the 0. So in this case, just 8. So if we set this equal to 40 as per what we have here, then what would, if we go ahead and solve for x right quick, what do we end up with here? Go ahead. Yeah, go ahead. You had your hand up.
Natural log of 6.
Right. So what happens is that if we add 8 over to the other side and then divide by 8 here, then we get e to the x should equal 6 from this. And then if we take the natural log of both sides, we end up with x equals natural log of 6, which that will be our exact value for what our number of hours we need. But as the problem states, we now need to round to the nearest 100th. So plug natural log of 6 into a calculator, you should end up with 1.79 hours. Okay? And that's the value of x we need here. So that says 1.79 hours later, since 8 a.m., we will have 40 more bacteria in the system. Okay? We good with this? Right. Cool. All right, well, that's all I have for today. So this is a nice little review of 16010/Calc1 stuff. So I will see y'all next Friday when we talk about the first new concept, U substitution.